a satellite that gains energy moves to a higher radius and moves slower. What if a satellite loses energy? Its radius will go down, so which means that it would move to a closer radius. It's sometimes called a lower orbit, and its velocity will increase. So if it loses energy, its velocity will increase. If it gains energy, its velocity will go down. And if it loses energy, it moves to a closer orbit. If it gains energy, it moves to a higher orbit. Okay, so if you understand this, now I can tell you about a very fascinating application of this. Okay, so you can all recognize this planet. So this is the planet Saturn. Here you can see a magnificent picture of Saturn. The most striking thing about Saturn is its unbelievable system of rings. The ring system of Saturn extends from about 7,000 kilometers above the surface of Saturn to 80,000 kilometers above the surface. So if this is Saturn, suppose we are looking down on Saturn above the North Pole of Saturn, we would see that the ring system starts from somewhere over here, and this is about 7,000 kilometers, and it extends to 80,000 kilometers. So this is almost 73,000 kilometers, or approximately a good 45,000 miles or something like that. So it's absolutely vast, the ring, the width of the ring system, and compare that with the radius of the Earth. The radius of the Earth, the diameter of the Earth is only 12,000 kilometers. So this is several times the width of the Earth, the ring system of Saturn. And what are these amazing rings made up of? They are made up of chunks of ice. So they're 99.9% water ice. So they're chunks of ice orbiting Saturn. So that's what the rings are made up of, like billions and billions of chunks of ice of various sizes orbiting Saturn. Now, we talked about the width of the ring system. It's a stunning 73,000 kilometers, something like that. What is the thickness of the ring system? The thickness of the ring system is amazingly 10 meters. So just imagine something 73,000 kilometers wide, but only 10 meters thick. So the ring system of Saturn is very narrow, right? So all of these particles that are orbiting Saturn, all of these chunks of ice that are orbiting Saturn are confined within a thickness of about 10 meters. Okay, now there is amazing structure in the ring system, and you can kind of see that in this diagram over here. I mean, this is actually a photographic image, though it looks like a painting. You can see this amazing structure. There are gaps in the ring system. There are various density patterns in the ring system. It's just amazing. Here you've got a big gap. The reason for these gaps are pretty amazing, but I'd be talking all day if I tried to explain them. All right, so the point is that there is a lot of amazing structure in the ring system, right? It's all because of gravity. The way gravity works is because you have all that. All right, now I just want to point out one thing. So one of the rings of Saturn is called the F ring, and you can see that the F ring has a really sharp structure. You can see that the particles in the F ring are confined to this this narrow band. So you don't have any ring particles spreading out of the F ring. So they're all confined within the F ring. Why do the particles in this particular ring stay within the ring? Like why don't they just spread out and diffuse? So what forces them to stay within the ring? So the question is the following. Here is Saturn. Okay, I'll just draw. I'll just draw. Maybe Saturn is somewhere at the bottom. I'll just draw Saturn over here. And let's just focus on one ring of Saturn, which is the F ring. It is a band of particles that are orbiting Saturn like this. So this is the F ring. And what I'm claiming is that all the chunks of ice that make up the F ring, for some reason stay within this band. Why don't they drift away from the band? I mean, they're constantly colliding with one another. Why don't they just drift away from the band and spread out and diffuse? The reason is because of the existence of two moons of Saturn, which are called shepherd moons. So you have one moon over here, which is called the inner shepherd moon, and you have another moon over here, which is called the outer shepherd moon. And both of these moons are obviously also orbiting Saturn. So how do these two moons make sure that the ring particles in the F ring stay within the ring? Okay, so to understand that, we have to first think about the velocities of the particles. And let's just write down our conclusion from over here. When E goes up, the energy of a particle in orbit, when it goes up, what happens to its velocity? Its velocity goes down and its radius goes up. I mean, the radius of orbit goes up. And if the energy of a particle goes down, its velocity goes up and its radius goes down. So this we just concluded from the formulas for kinetic and potential energy. We are going to use this fact. All right, now consider what happens if a ring particle comes out of this ring. Everything is orbiting this way, let's say, in the counterclockwise direction. So suppose a ring particle drifts out of the ring and it gets over here. Here is our divergent ring particle. I'm drawing that as a black closed circle. Now, first of all, let's consider the relative speeds. Which do you think, let's call this 1, 2, the ring particle is 2, the particles in the ring, let's just take a particle that's inside the ring as 3, and the outer shepherd moon as 4. So I'll make shepherd moons like this. Which of these is moving fastest? The 1, 2, 3, or 4? Clearly, 1 would be moving fastest because it's closest to Saturn. Remember our formula for orbital velocity? V is equal to square root of gm divided by r. So if r is lowest, then V is going to be highest. And so the inner shepherd moon is moving the fastest. The divergent ring particle, which strayed out of the ring, is next fastest. The ring particles themselves are moving slower, and the outer shepherd moon is moving slowest, right? All right, so the particle that strayed out of the ring, which is indicated by 2, would be moving faster than all the particles inside the ring, right? However, the inner shepherd moon would be moving much faster than the ring particle. So every now and then, the inner shepherd moon would pass by particle 2, and it's the inner shepherd moon is a large moon, right? And and this particle is just tiny. It's like a pebble. So it's going to feel a force as the inner shepherd moon passes by it, right? So that tug due to the inner shepherd moon, every time it passes by ring particle 2, will give extra energy to ring particle 2. And what happens to a ring particle when it gets extra energy? If it gets extra energy, its radius goes up and its velocity goes down. So eventually, as it keeps getting more and more extra energy, it will go back into the ring. The same exact thing happens if a particle gets out of the ring on the other side. So suppose a particle, let's call that 5, gets out of the ring on the outer part of the ring, right? So now 5 would be moving faster than the ring particles, sorry, slower than the ring particles because it's got a larger radius, but faster than outer shepherd moon, which is number 4, right? So what's going to happen is that um, when 5 passes by the uh, outer shepherd moon, every time it passes by the outer shepherd moon, it's going to feel a tug from the outer shepherd moon, which is going to pull it backwards because the outer shepherd moon is moving slower than it, right? So as it passes by it, it's going to feel a pull to the, it's going to feel a backward pull, and so that's going to take away energy from it because it's like a drag force. It's going to take away energy from it, and so as it loses energy, what happens to a particle in orbit? As it loses energy, it speeds up and moves to a lower orbit, and so this will also eventually move back into the ring. And so any particle which diverges from the ring eventually gets back into the ring as a result of these two shepherd moons. And this is absolutely amazing. The presence of the shepherd moons was first postulated by scientists because they were amazed by how sharp this ring looked. So it looked like there must be some influence on the ring which maintains its sharpness. And so they suggested that it's probably shepherd moons, and then these shepherd moons were actually seen and photographed. Okay, and yeah, so here's a picture of one of the shepherd moons. Okay, so that was just an application of of the relationship between the total mechanical energy and the velocity and radial distance of an object in orbit, and that concludes our discussion of gravity. I must briefly mention here that Newton's law of gravity is not the full picture of gravitation. Einstein realized in the early part of 1900s, between 1910 and 1920, that there is something wrong with the way we view the gravitational force. And he realized that gravity is not really a force at all, but a manifestation the uh, of the warping of space and time. And so gravity is not really a force, it's a fact that if an object is sitting in warped space time, um, the way it's going to behave is what we interpret as a gravitational force. And so that idea is called the general theory of relativity. And that's obviously way beyond the scope of this course. But I just wanted to briefly mention it before concluding.